Hello, everybody. Welcome to this section. I'm very happy to be here. I would like to thank the organizer for the opportunity to take this conference. Well, we have some formal announcement. The meeting is being recorded and live streamed. If you don't wish to be recorded, please keep your microphone and camera off and use the chat button for any questions. Live transcript will be active. If you can turn this off through clicking the live stream button on the bottom of your screen. Okay. Now we can go to the mathematics. Well, the first speaker this morning is Amiot from University of Grenoble, Alpes, and she's going to speak about indecomposable objects in the derived category of Skew-Gentle algebras. Claire, please.
Thank you very much, Sonia, and thank you everyone for being here. So let me share my screen. So is it okay? Yeah, maybe. Okay. Okay, so today I will focus on this question that if we start with K, an algebraically closed field of characteristic different from 2, and we take a skew-gentle algebra on it. So I won't recall the definition of a skew-gentle algebra, but I will give a bit more detail later. And my aim is to describe the indecomposable objects of the derived, bounded derived category, but using a topological model or a geometric model, if you prefer. So this question has already several works on this question. So the first one goes back to Becker, Marcos, and Merklen in 2003. But what they did was, well, they did not use a topological model. So they use a combinatorial description of this indecomposable object of this derived category. The second work I should mention is the work of Labardini, Valdivieso, and Schroll of last year. And I will speak about this work a bit later, but well, they use different methods. So I think it worth to explain you how I can solve this problem. And for today, I will just concentrate on special objects that I will call bound objects, because I think this is the most interesting part of this classification. So first, let me start with some motivating facts about this problem. So there are mainly two motivating facts. The first one is that this question has been solved for gentle algebras by a work by Hopper, Plamondon, and Schroll. And so what they do is that, so roughly speaking, so to lambda a gentle algebra, they can construct a marked surface. So S will be a surface with boundary, and M will be a set of marked points on the surface, and D, it is what is called a dissection. So I won't give you the precise definition of a dissection, but it's a certain collection of arcs on S, and an arc is a curve with endpoint in being marked points. So endpoints are in M, and yeah, so these are arcs on the surface. So the second result is a joint work with Thomas Brüssler And so what we did is that so first we start with the Skew-Gentle algebra, and we can associate to this Skew-Gentle algebra another algebra, lambda tilde, which is gentle, and together an automorphism of lambda tilde of order 2, such that the following occur. So first, lambda then is Morita equivalent to lambda tilde Z2, which is the skew group algebra of this gentle algebra lambda tilde, and the Z2 action comes here from this automorphism of order 2 of the algebra lambda tilde. And here, I mean, this is not a result. This is due to, of course, this justifies the name Skew-Gentle, and this is due to Geiss and de la Peña in their original definition of Skew-Gentle. So here I should already point this out. And but so what we did with Thomas is that we understood this action of sigma. We can understand this action at the level of the surface. So to lambda tilde, following Hopper-Plamondon-Schroll result, what we can do is to associate a surface that I will denote by sigma S tilde, and this automorphism sigma, we can lift it into a homeomorphism of the surface, which will be also of order 2. And then a natural topological model for this derived category of dB lambda would be to take the quotient of S tilde by this homeomorphism of order 2, and the projection of the marked points and of the corresponding dissection. So P here is just the projection of S tilde on the quotient S tilde by sigma. And the thing here is that this homeomorphism has some fixed points. So then S is not a surface, but it's an orbifold surface. Okay, so then the idea is that combining this and I should have mentioned it before, but in the work of Hopper-Plamondon and Schroll, they can describe the indecomposable object of the derived category of dB lambda in terms of curves on this marked surface. So combining these two, it's natural to expect to get a nice description of the object of the derived category of this lambda. So let me now be a bit more precise, and I will tell you some useful results. So the first one is, again, it's due to Hopper-Plamondon and Schroll. So what they do is that, so we start with lambda tilde gentle, and we can associate a dissected marked surface. And then what they prove is that there is a bijection between certain indecomposable objects in the derived category of dB lambda tilde that are called the bond objects with a certain set here. So let me explain what is this set. So the set here is a set of things that gamma into bracket n and lambda. So what is gamma into bracket? It's this is a conjugacy class of an element, a closed curve on the surface S tilde, so of an element in the fundamental group of S tilde. And this will be a grading, so I will try to explain you a bit what is a grading in 1 second, and this lambda is a parameter. So what is a grading here? So roughly speaking, so the dissection d tilde, so recall that this is a collection of arcs on the surface, and it cuts out the surface into polygons. And now if we take a curve, well, the conjugacy class of a closed curve on the surface, so we can take it minimal with, so up to homotopy, we take it minimal with respect to this dissection. And then a grading on this curve, it's a collection of number for each crossing of the curve. So this would be gamma. For each crossing of the curve with the arcs. So here I put a number, which is n1. Here I put a number, which is n2. And n2 will be n1 plus or minus 1, depending on where the boundary is with respect to this curve, whatever. But there is a rule to construct such a grading on a closed curve. One remark, however, is the fact that not all closed curves are gradable. So only certain closed curve admit such a grading. But this is well defined up to this free homotopy, so this up to conjugacy class of the element in the fundamental group. And finally, let me just explain you what is this equivalence relation here. So the equivalence relation, because it plays an important role for later in my talk. So to such triple gamma, n, and lambda, it's equivalent to the inverse of the curve, gamma minus 1, then the same grading, but here we have to take lambda minus 1 to get a nice bijection, a natural bijection between the curve. So this is the equivalence relation. And yeah, maybe I will just give a name of this map, this bijection, and I will call it B tilde. Okay, B like bounce. Okay, so this is the first useful result, and this is the result we want to generalize in the context of skew-gentle algebras. So the second useful result goes back to Reiten and Ritman in the 80s. So what we can do in this setup, so if we start with lambda skew-gentle algebra, and if we associate this Z2 gentle algebra associated to lambda as Geiss and De La Peña defined, then a corollary of Reiten-Ritman's result is that there is a bijection between indecomposable object in dB lambda and certain object in the derived category of dB lambda tilde. So namely, if you have an object here, X, which is, okay, this sigma induces an action. So it's an automorphism of lambda tilde. So it induces an action on the category dB lambda tilde. And if you have an object which is not isomorphic to its sigma of it, then you take the orbit. So to each orbit, you can associate one object in this category. And if you have a fixed object with respect to this action, then you get two objects in this category. So then that's why we get this plus or minus one here. And this bijection, in fact, comes from functors from dB lambda tilde. We can construct different functors, but in particular, we can construct a functor here that I will denote by F, which will send this X or this X sigma to an indecomposable object in here, and which send X here, such an X here, to the sum of two indecomposable objects in this category. So that's why this bijection is constructed. And then we have to prove, of course, that F is dense, like reach any indecomposable object in this category. So the idea is to use this result to describe the indecomposable object in dB lambda. And the first thing that we have to check is to understand this action on the category, this action of sigma on the category in a topological way. And this is not surprising and actually not very difficult to prove. That if I take, I take a bound object associated to gamma n lambda, and now I twist it by this sigma in the derived category, and what I get is a bound object again, but which is associated to sigma of gamma, the sigma of n, well, n composed with sigma, and the same parameter lambda. So of course this result is quite, I mean, again, it's just a verification, but one has to check this. Okay, so but now we have this result. So we have all the tools to answer my original question, because now we understand topologically how the action on the derived category works. And so then we can solve the original problem, but then we can, yeah. So first remark is that we have to understand when bound objects are our fixed point under the action of sigma. And what we can check is that, okay, just following the lemma. So if we take a bound object, which is a fixed point, what does it imply? It implies that either gamma is equal to sigma gamma, or gamma minus 1 is equal to sigma of gamma. But then, because of the equivalence relation I explained just before, we should have lambda equal lambda minus 1. So we get lambda equal plus or minus 1. And this will play the fact that here the parameter plays a role in the fact that the bound object is a fixed point or not under the action of sigma. Okay, but so now we have all the tools to solve the question, except that here what we can do is to describe the indecomposable object of dB lambda, but in terms of curve on the big surface S tilde. But what we would like is to understand this indecomposable object in terms of curves on the orbifold surface. And here we have to work a bit. So let me state the main result here. So, okay, so we start with the Skew-Gentle algebra, and we associate this dissected marked orbifold. And then the bound objects are in bijection with these three different sets. So the first one is very close to the previous one. So it's just a conjugacy class of a certain element in a certain fundamental group gamma. But here we have to assume that gamma is not conjugate to gamma minus 1. And here, when gamma is conjugate to gamma minus 1, we have two different cases. So one is when the parameter is different from plus or minus 1. And in the case where the parameter is plus or minus 1, we get a second tagging by another plus or minus 1 here, which comes from this Wright and Ritman theorem. So what is here, what is pi 1 of what I denote orb of the curve of the surface, sorry. So yeah, this is a conjugacy class in a certain group, and this group is just the pi 1 of the surface minus the orbifold points, and we mod out by the fact that around an orbifold point, if the curve goes like this, then it's the same as going the other way around here. So then this fundamental group here is, yeah, so then you get some torsion in this fundamental group. So this makes the thing a bit more complicated. A few remarks here. So the first remark is that in this work by Labardini, Valdivielso, and Schroll, what they use the result of Baker, Marcos, and Merklen, and I don't use this result in the proof of the theorem. And moreover, what makes the thing different is that they describe homotopy strings and homotopy bands. And actually, homotopy strings and homotopy bands are not always indecomposable. So in the previous result I gave, we really get indecomposable objects. So we know which one are indecomposable or not. The second remark is that there is a similar also result due to Q, Zhang, and Zhu for the graded case, but it did not appear yet. So I don't know which kind of methods they use to get the result and which exactly result they get. So now I will try to explain you a bit how the bijection works in the theorem. So let me start with a graded curve here together with a parameter. And the first case is when this curve is not a torsion element up to conjugacy in the group. So let me draw an example of such a curve here, gamma. So here, what did I draw? Okay, sorry, I go too fast. So here is S is my orbifold surface. So it's a cylinder with two boundary components, some marked points on it. And this is the orbifold point. And I associate these twofold covering of the surface, which will be a sphere with three boundary components here. And sigma here is just the rotation around this axis here, and you see that there is one fixed point which corresponds to this orbifold point. And when you mod out S tilde by this sigma, you get S. So now I start again with my grain curve and I lift it in S tilde. And the first nice case that can occur is that I get a gamma tilde, which is closed. And if I take a sigma of it, I get another closed curve, which is this one. Okay. So now, how do I construct my bijection? So first, you have to trust me that I can lift also the grading. It works nicely. So this n gives a grading. This n here gives a grading on the corresponding curve, gamma tilde and sigma gamma tilde. And now I take B tilde of gamma tilde and tilde and the same parameter lambda. I apply my functor f, and what I get is one indecomposable object, which will be my B of gamma and lambda. Okay, so this was the easy case. So now the second case is, again, I start with a curve satisfying this, but now when I lift up the curve here, I don't get something closed. So, okay, I lift this curve gamma and I get a curve which is not closed. But what I can do is to take sigma of gamma tilde, and here I get the sort of second half of the curve, and now I can form a curve alpha tilde, which is gamma tilde composed with sigma gamma tilde, and which is closed. And moreover, this curve satisfies that the conjugacy class of sigma alpha tilde is equal to alpha tilde. So now what I can do is that I take the object corresponding to this alpha tilde with a lift of the grading and tilde again, but then I take the square of the parameter lambda square, and this object, since it satisfied this is a fixed point on the reaction of sigma. So when I apply my functor f, here I get two objects, and my two objects will correspond to, so this will be B of gamma and lambda plus B of gamma n and minus lambda. Okay, so this is the second case that can occur. So, okay, and now the third case is when you have when you start with a curve which is conjugate to its inverse here, and this is typically the case when, okay, let me draw such a curve. This will be a curve like this. Okay, this will be gamma, such a curve. And then if you lift it here, what you get is something like this. This will be gamma tilde. And then one can check that this curve is again a nice curve on the category, which satisfies that sigma gamma tilde is gamma tilde minus 1. So now what we can do is we take the object that corresponds to this gamma tilde n tilde and lambda, and then depending whether the parameter is so if the parameter is different from plus or minus 1, what you get here is one indecomposable object, and if the parameter is plus or minus 1, here what you get is two indecomposable object. So that's why in the theorem, so let me show you the theorem again. So here in these two sets, you have to, so if gamma is equal to gamma minus 1, then you have one object for each parameter different for plus or minus 1, and two objects for each parameter equal to plus or minus 1. Okay, so if, yeah, do I have like 2 minutes more, or should I stop here? Is it okay if I add a few words, Sonia? you, you don't answer, so I don't know, maybe.
Yes, yes, you
Yeah,
can take
okay.
it.
Yeah, so I just wanted to add a remark at the end about tagged arcs. So the thing is that when you start with a curve such that gamma is equal to gamma minus 1 and gamma square is different from 1, so I didn't speak about this condition, but okay. Then it means that the curve is typically like this. So you have two orbifold points and then you get a curve. This will be a gamma satisfying such condition. Okay, so as in the picture before. So okay, here it's the same orbifold point, but this is still a curve as I draw here. So then it's natural to think about this curve as an arc between the two orbifold points. And for such a curve, remember that for the parameter plus or minus 1, then you get 4 different objects because you have 2 values for the parameter plus or minus 1, and for each you get 2 curves. So then you can put some tagging on the curve and you have 4 possibilities for the tagging, so you get 4 different objects. But so this is very nice, but this is also a bit dangerous because typically, so look at this situation. So where you start with such an arc like this, so which the corresponding closed curve will be something like this. Okay. And imagine that you start with his friend, which is another tagged arc like this, then the corresponding curve will be, okay, did it wrong. Okay, yeah, I sorry about this. I shouldn't worry. Okay, this is better. Okay, and what you can check is that these 2 curves, they are the same in the orbifold fundamental group, because here what you can do is that here you have a fishtail around this cross and you can smooth it or what, and what you obtain is this curve. So and if you do it again, you get this curve. So in fact, these 2 tagged arcs, they are equal and they correspond to the same object. So it's just to say that we have to be a bit careful with tagged arcs, but yeah, okay. So thank you very much. I'm sorry for having 2 minutes of delay.
Well, are there any questions, comments? I don't see any questions. No questions?
There's a question in the room.
There's a question in the room.
Can you hear me, Clara?
Yes, more or less. Yeah.
There's a microphone here, sorry. Does your model, can you use your model to say anything about morphisms and extensions?
I hope so, yeah. For the moment, no, but of course we can use it because this functor by Reiten and Ritman preserve homomorphism and extensions. So of course you get then using, so in the OPS, in the gentle case, we can describe, so they describe the morphism spaces in terms of intersection of curves. So you can of course use this through these functors, through this functor f, to get some information for on the corresponding object. But then of course you have to be careful with this special I mean, for the nice arcs, it should be easy to do, but for this strange arcs here, then of course one has to be more precise in the bijection and to see when they are compatible or not, and this is, yeah, this needs to be done, but using height and Riemann thing, we can have lots of information already.
So I mean, this the writing Riemann function is function f, right?
Sorry, what did you say?
The writing Riemann function is f on the previous slide.
Yes, yes.
What kind of function is that?
It's just a tensor product. It's just so you have, so lambda tilde is z2 is lambda. So then you can construct from dB. You just, yeah. So it goes the other direction. Sorry. It's just a tensor product by lambda tilde z2 over lambda tilde. So it's just a nice functor. And so it's not so nice in the sense that here, in fact, when you apply this functor, you end up in the category dB lambda tilde z2, which is not strictly speaking dB lambda, but then you have to apply a Morita equivalence to get this. So it's, yeah, it's not. But still, I mean, it preserves homomorphism and extension. But what is not clear, for instance, is that so in the category of dB lambda tilde, typically you may have, so if you take a homogeneous tube here, you can end up in this category with either two tubes. Well, in case this is a fixed point, you can either end up with two tubes or with a tube of rank 2. And this is not clear when it is the case. I mean, this is really a functor linking like dB A, lambda of type A and dn case, or an tilde with dn tilde case. So sometimes you have tubes that gives two tubes, and sometimes you have tubes that just gives rise to a big tube of rank 2. So, and then you may have extension. Okay, here the object here, they are rigid, and here it's not rigid. But here they are not rigid. So yeah, to check compatibility and extension is not for the spatial objects. This is not so easy, but I think it can be done, and I hope I would like to do it. But yeah, I don't know who else is working on it at the moment. So maybe there are also some results about this already.
Okay. Are there more questions? More questions? Well, it's not, we thank Claire again. Well, we thank Claire because we didn't thank before for this very nice talk. Thank you.
Thank you.